Hello and welcome to my video on linear correlation and regression. So what you're going to learn here is how to do correlation, how to find the coefficient R, how to perform a correlation, how to do a hypothesis test, and distinguish between correlation and causation. Now this P, what looks to be a P, is really a rho, Greek letter rho. So a correlation is a relationship between two variables. The data can be represented by ordered pairs. Now x is the independent or explanatory variable. Now I also like to think of x as the input variable. Y is your dependent or response variable. I also like to think of the y variable as the output. So we can do a scatter plot here. So for negative linear correlation, as x increases, y would tend to decrease. That's negative linear correlation. If you have positive linear correlation, that's where both variables increase at the same time. Now, no correlation means there is just really no seeming pattern. And nonlinear correlation, we're not going to touch that in here, but you can do nonlinear correlation. All right, so this little part here tells you how to enter all of the data in your calculator, and as well as to do all the linear correlation and regression stuff. So make sure you read through this. So one thing I'm going to do is, if I go to mode, I want to go down to stat diagnostics and make sure that is turned on. Now, this is the data that's in the list, and this all shows you how to do that. Now, let's say an economist wants to determine whether there's a linear relationship between a country's gross domestic product and carbon dioxide emissions. Now we're going to do a scatter plot. I'm also going to go ahead and do the correlation. So in these notes, it tells you how to do that. So yeah, it tells you how to do that. So the nice thing is, yeah, my data is already entered. I'm using L1 and L2. L1, list 1 is the GDP in trillions of dollars, and L2 is the CO2 emission. Now what I'm going to do is I'm going to do a linreg on that. Whoops. And I'm not going to store the regression equation right now. Actually, you know what? I am. So what I'm going to do, you know what? No, so this is the linear regression. Now, I'm going to copy that over to this document. Now, we're actually going to see this a little bit later in the course. I mean, we're going to be using this a little bit later. Now, what I'm going to do is I'm going to make a plot. So I'm going to go to plot 1, turn it on, X list and Y list are L1 and L2. And if I want zoom stat, I hit zoom 9. And so this is the data here. So what the data appear to be, the data appear to have a positive linear correlation. Now, the data do have a positive linear correlation. Now, one thing I'm going to do, I'm actually going to go back to stat and linreg, and I'm going to go to store regression equation. I'm going to hit vars and scroll over to yvars function y1. Then I'm going to recalculate it. Now, it gets the same thing, but when I go to graph, it's going to give this. It's going to give the scatter plot with the line of best fit. Now, that line of best fit, how that's determined, calculator does that for you. So there appears to be a positive linear correlation. That's really all we needed to do for this one. Now, we're going to do this one here, Old Faithful, which is located in Yellowstone National Park. So we're actually going to change some things. So for LinReg, the data are in L3 and L4. So I'm actually going to go ahead and put those in, and then I'm going to calculate it. And we get this. Now, we definitely will be coming back to things when it comes to this. And we will be using this again. Now, here's the thing. Yeah, let me just make sure I believe, yeah, L3 and L4 have that data. Now, I'm going to go to stat plot. I'm actually going to go to y equals first. I'm going to delete this. And I'm going to go to stat plot, and then I'm going to put my x list and y list is L3 and L4 respectively. And let's see what we got. Now, if I graph it, we don't see anything. We have to zoom 9. And as you can see here, the data definitely appear to have a positive linear correlation. So that's how the data for this one are going to appear. So yeah, it goes to show that this has a positive linear correlation because as x increases, so does y. So this correlation coefficient measures the strength and direction of a relationship between two variables. The symbol r represents the sample coefficient, and as you can see, r is given here. If we have positive correlation, r will be positive. If we have negative correlation, r will be negative. No correlation is where r is 0. Now, there is a possibility for nonlinear relationship, and in that case, r could be positive or negative. But again, we're not going to be dealing with any nonlinear data here. So if you look here, look at this formula for calculating r. Step back and look at that for a minute and be thankful that you actually don't have to calculate that you're going to be using the graphing calculator. So r goes from positive 1 or negative 1 to positive 1 inclusively. Now, if r is negative 1, there's a perfect negative correlation. If it's positive 1, there's a perfect positive correlation. If r is exactly negative or positive 1, to me, the statistician in me would say, hey, that's a cause for concern. That shouldn't be. So, now the difference between weak and positive correlation is the magnitude, how close it is. Generally, obviously, the closer it is to positive or negative 1, the stronger the correlation is. So if we calculate those coefficients for those on pages 2 and 3, actually I think I did move those up a bit. We've already calculated those. Now, you can do them by hand, but why bother? Now, once the sample correlation coefficient r has been calculated, we need to determine whether there's enough evidence to decide that the population correlation coefficient rho is significant at a specified level of significance. So, if r, the absolute value of r, is greater than the critical value, we decide that the correlation is coefficient, the correlation coefficient is in fact significant, and what this means is there is evidence of a linear relationship. So there would be evidence of a linear relationship there. So basically, here is a table of the critical values. Now, we are going to also correlate this to a t calculation. We can do that here, which I think is pretty neat. So, for instance, if we had 5 pieces of data in the sample, and we have a level of significance. Now, it depends on whether it's one or two-tailed. So if we look at 0.01, 0.95 nuts. So yeah, two-tailed, it would be this one, obviously. So the absolute value of R would have to be greater than the value given in this table. So that's how we are going to do that here. So using the Old Faithful data, we used 25 pairs of data to determine that R was 0.979. So an alpha value of 0.05. So really, hypothesis tests for correlation should be one-tailed. Now, we're going to formalize this in a bit here, but let's see here. 25 pairs of data. So if it's 25 pairs of data, we have to look here at alpha equal to 0.05. So 25 pairs of data, and when alpha is 0.05, the critical value is 0.3365. And since R is obviously greater than the critical value, the correlation coefficient is significant. So what this means now is we have evidence of a linear relationship, or let's say a linear correlation between, let's see, what were those two variables for Old Faithful? We go back up to that real quick. Duration and the time between eruptions. So between the duration of eruption and the time between eruptions. So a hypothesis test can be used to determine this. Now, a left-tailed test would be that rho is less than 0 for significant negative. For right-tailed, it would be positive, and for two-tailed, it would just be not equal to. I really haven't seen much practical use of two-tailed hypothesis test for correlation. Now, we can actually calculate T based on this. T is equal to this, and it'll follow a T distribution with n minus 2 degrees of freedom. So for this one, we're going to do a one-tailed test. So the null in the alternative, the null would be that, the alternative would be that there is a positive linear test, or positive linear relationship, and we could just say less than or equal to, or just equal to 0 for no linear relationship. Alright, so what we have here is we got R equal to 0.8825. Now, if we count the number of pairs of data, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There's 10 pairs of data. So what we can do here is, 10 pairs of data, we'll use alpha equal to 0.05. So 10 pairs of data, alpha equal to 0.05, and we'll just do the one tail, and the critical value is 0.5494. So what this means is, since the critical value is 0.5494, since the absolute value of R is greater than the critical value, we reject the null. And what that means is there is evidence of a linear relationship between GDP and CO2 emissions. Now, I'm also going to calculate T here. So, based on that, this formula for T, which is R over the square root of 1 minus R squared over N minus 2. Now, keep in mind, N is the number of pairs. So, there were 10 pairs of data here. So, what we're going to do here is we're going to go straight over to the graphing calculator. Now, I should add that, yeah, we have 8 degrees of freedom. So if we quit out of this, I'm going to set up a fraction here. I'm actually going to kind of nest them. So R, which is 0.8825, then we're going to have a square root. And then inside that square root, we'll have this. 1 minus 0.8825 squared, and that's divided by n minus 2, which is 8. We get a t value of 5.307. Now, since the alternative hypothesis was greater than, this is a right-tailed test. So, if we do TCDF from 5.307 on, we'll do TCDF from 5.307 to a big number with 8 degrees of freedom. Now remember, it's always got to be that. So we'll go into the distributions. So 5.307 to some big number with 8 degrees of freedom, and we have 3.6 times 10 to the negative 4. Basically, it is 0.00036. So it's definitely a rejection. Now, believe it or not, you could actually go to stat tests and you can actually do a linear regression t-test. And for the alternative hypothesis, we thought it was greater than 0. And we'll go ahead and calculate that. And we see exactly the same thing. You can actually do confidence intervals based on the slope as well. You know, the slope, which we're going to be talking about in just a few moments. So, correlation and causation. So the fact that two variables are strongly correlated does not necessarily imply a cause and effect relationship between the two variables. If there is a significant correlation, you should consider the following possibilities. Is there a direct cause and effect relationship between the variables? You know, does X cause Y? Or does Y cause X? Now, is it possible that it could be caused by a third variable or other variables? Or is it possible that the relationship between these variables just may be a coincidence? Well, here's some data, body weight and backpack weight. So I'm going to enter these into L5 and L6. So the body weight, 120, 187, 109, 103, 131, 165, 158, 116. We're going to see if there is a correlation between body weight and backpack weight. Now, it might seem, you know, you might think, oh yeah, heavier the person, the heavier the bag. So let's do the not 1var stats, but Linreg this time for L5 and L6. So if we calculate that, and I go ahead and put that onto here, what we need to do, we're going to do, so we think that there is a positive linear relationship here. Well, let's test that. Let's test that fact. So for the null hypothesis, rho will equal 0. For the alternative, rho will be greater than 0. So R is 0.7947. Now, if we have n equal to 8 pieces of data, that means we have 6 degrees of freedom. So, if we go to 6 degrees of freedom, one-sided, where alpha is 0.05, the critical value is 0.6215. So, and if we calculated the t, we would get a similar conclusion. So, we do have evidence of a linear relationship between body and backpack weight. Now, yeah, just because there is a relationship doesn't necessarily mean the heaviest person is going to have the heaviest backpack. It could just, it's true, they probably have more ability to carry a heavier bag, but, depending on where you are, you, like, at a college, I know, like, when I went to college, I carried a heavy bag around because I lived at home, and, I couldn't just go home and get something. I was basically stuck there all day. So, in other words, yeah, there could be hidden variables or other variables behind this. Alright, so let's move on. So how to find the equation of a regression line and how to predict. Well, believe it or not, all of this regression stuff, we've already kind of done that here. And we're just going to use the calculator to figure out some of this stuff. Now, there is one other thing that I am going to expect you to know, and that is a residual. The residual is the difference between an observed y value and a predicted y value for a given x value. So what happens here, we have, the reason we do residuals here, if we look at the graph, the line of best fit will not go through, obviously, every point here. So every point will have a residual. Some points might be smack dab on the line, but we'll get to that as it happens. Now, the regression line for the line of best fit is a line for which the sum of the squares of residuals is a minimum. Now, your calculator will actually figure this out for you, which is nice. Y hat is the predicted y value for a given x value, and m is the slope, and the b value is the y-intercept. Now, the nice thing is, your calculator will do the linear regression, will do this equation for you. Now, it won't actually tell you what the equation is, but rather, it will actually tell you what the... Now, instead of m, your calculator gives it to you as a and b. So basically, the equation for the regression line is y hat equal to 196.15x plus 102.29. Now, one thing we can do here, now for this, I actually did do this to 3 decimal places, but we can, 2 should be really enough, unless it's less than 1, just kind of use common sense here. Now, instead of this, I'm actually going to change this one here for 2.9 trillion, and I want the residual. So, the regression equation for the gross domestic products in trillions of dollars is this here. Now, we can use the equation to predict the expected carbon dioxide emissions. So, for 1.2 trillion, y hat would be 196.15 times 1.2 plus 102.29. So when we go to figure that out, we get 337.67 millions of metric tons. Now, for the same one, for 2.9 trillion, I'm also going to ask for a residual here. So the predicted is 196.15 times 2.9 plus 102.29. So the predicted CO2 emissions, let's see what that's going to be. 671.13. Now, the actual, or the observed amount, was 415.3. So, if you remember, residual is the observed minus the predicted. Observed minus the predicted. So 415.3 minus 671.13. We get a residual of negative 255.83. Now, what we're going to do here is we're going to use the calculator. I'm actually going to do the linear regression on L1 and L2 for the CO2 data. And I'm actually going to go ahead and store this linear regression equation to Y1. So we'll store that. We calculate it. Let's do that stat plot again. This time we do L1 and L2. And if we hit zoom 9, what we see here, if we hit the trace button, if you hit up or down, you can either get the plot or the equation. Now, if we go to this, for 2.9, we saw that the actual was 671.12. And if we hit down, let's see here, 2.9 was 415.3. Now, there is a reason I did this regression again, because what I'm going to do here is, if I highlight this blank list, I'm going to hit second and list. I wanted to hit second and list, and I'm going to choose resid. Now, probably have been better. So if I go to 2.9, I know it's a little off here. So the residual is negative 255.8. So it does show the residual, which is pretty nice here. So for this next one, this is going to be a long example here where tuition at the University of Pittsburgh is given below by this table. X is going to be the number of years since 2000. So Y will be the tuition. So we're going to do a linear regression test. So what I'm actually going to do is, if we let X be the number of years since 2000, now sometimes you might actually be given the year like you'll see in a later example. So we'll have 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10. And for L2 is the tuition. Yep, 6512, 7134, 8543. Yep, tuition does go up. And in case you're wondering, this is the in-state live-at-home tuition, as I called it. So this goes from 2000 to 2010, or 2001 rather. So we think that this is just going to be a one-tailed test. So we think there is a positive linear correlation. And for the null, there would be no linear correlation. So that's what we'll get here. So we're going to determine the equation relating the tuition and the years. So let's do the linear regression for that. And we do that. Let's just round that to 2 decimal places rather. So y hat is going to be $966.04 x plus $4,212.20. Now, even though I didn't actually say anything here, the practical meaning of the slope. Practical meaning of the slope for each year, which is the y variable, we expect tuition to rise by $966.04. So that's what we would expect. So the correlation coefficient R is going to be 0.9831. So the test statistic, rounding to 3 decimal places, T will be 0.9831 over 1 minus 0.9831 squared over, let's see, there are 10 pairs of data, so this will be 8. So if I go to do this in the calculator real quick, I get to set up a fraction here, 0.9831. 1 minus 0.9831 squared over 8, and we get a t-value of 15.189. So if we want to determine the p-value, the p-value is basically going to be 0. But let's do the TCDF. So 15.189. So we reject the null. We have evidence of a linear relationship between tuition and number of years. And at that, it's a strong relationship. So if we want to predict the tuition for 2019, now for 2019 we take 966.04 times 19 plus 4,212.2. So if we go ahead and do that real quick on the calculator, plus 4212.2, the tuition is going to be $22,567. Now, according to what I'm reading, the actual tuition, it's not on the list, the actual tuition in 2019 was $19,700. So I would ask for a residual, which is observed minus the predicted, 19,700 minus 22,567. And the residual is going to be negative $2,867. That's what we're going to get for the residual. All right, so we're going to go ahead and do a couple more regression problems here, where we're going to let X be the number of years since 2000 here. So enrollment at Ambridge High School So for the lists, instead of the year, we're going to put 1, 3, 4, and so on. So that's what we're going to do. We're going to put these in the lists. So let's see. We'll have 1, 3, 4, 7, 9, 11, 13, 16, 19, and I'll just end up deleting this. I'm going to clear the list here. Newsflash, do not ever hit delete. Remember what happens. So 2450, 2310, 2296, 2155, 2101, 1989, 1975, 1887, and 1800 students. Yeah, Ambridge is actually a real place outside of Pittsburgh. They're actually the headquarters of American Bridge. Little fun stuff. Alright, so for this, we're going to do everything here. So we're going to determine the model for the line of best fit. So the data is in the list. So we're going to do a linreg, and I'm going to go ahead and store this regression equation to y1. So if I choose y-vars function 1, we're going to get this. Now this is going to be a negative one. So for this one, I'm actually not going to round. Well, yeah, I'll round to 2 decimal places. So the model for best fit, y hat, is going to be negative 34.87x plus 2428.62. Now r in this case is actually going to be negative, is negative 0.9878. So the practical meaning of the slope in the context of the problem, basically for each year that goes by, we expect to lose 34.87 students per year. So that's how that's going to work. So the hypotheses, this time we're dealing with a negative correlation. So for the alternative, rho will be less than 0, and for the null will still be equal to 0. So we can do this actually 2 different ways. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 pairs of data for this. So what we're going to do, if n is 9, that means there's going to be 7 degrees of freedom. So what we'll do here, t will equal negative 0.9878 over the square root of 1 minus negative 0.9878 squared over 7. So when we go to figure that out for t, so for this one, we're going to get a t value of negative 16.782. So basically, the p-value will be 0. Now, if we go to alpha equal to 0.05, and we have a critical value, let's see, the degrees of freedom is 7. It needs to be 0.58 or higher. So basically, we reject the null. We do have evidence of a linear relationship between enrollment and years. So now we're going to predict the population of the school based in the year 2025. So negative 34.87. So let's get this here. So negative 34.87 times 25. Now remember, and that'll be plus 28.62. So let's see what that is. We're going to have 1,557 students. Enrollment will have declined there. Now in 2050, let's see here. So we need to replace the x with 50. So when we go ahead and do that, what we get here is, we get 685 students. So enrollment has really gone down. So based on the model, when do you think the population will fall to 1,500 students? So we know it's declining. So we know it's going to be before 2025 because, well, no, it's going to be after 2025. So what we have to do here is simply take negative 34.87x plus 28.62, and we set it equal to 1,500. Now we're going to get x here, but remember, you have to add 2,000 to that. So x is going to be, to the nearest whole number, 27 or 2027. So I would allow you some wiggle room on this. Now we'll do the same thing for 500 students. So for 500 students, we're going to get 2055. So probably by then it would merge with someone. Scatter plot, line of best fit. So now 2007. So the actual value for 2007 was 2155. So the expected value would be negative 34.87 times 7 plus that. So the expected value would be 2185. So the residual is observed minus expected. 2155 minus 2185. The residual would be negative 30. Alright, so I'm going to end this video for this, so I hope you enjoyed it. I know I did. Alright, so enrollment here at Ambridge High School is shown below. X is going to be the number of years since 2000. We're going to answer the following questions below. So we're not going to put the years in for X on the graphing calculator. Instead, for X, what's going to go in for X in each case would be 1, 3, 4, 7, 9, 11. Let me get a thicker pen here. 13, 16, and 19. So what'll happen here is I'm going to put these into the calculator like so. So what I'm actually going to be doing here is under Stat, edit, in L1, I'm going to put all of the year, I'm going to put X. So 1, 3, 4, 7, 9, 11, 13, 16, and 19. Now for L2, I'm going to put these enrollments. So 2450, 2310, 2296, 2155, 2101, 1989, 175, 1887, and then 1800 students. So I have all my data in the calculators now. So what I need to do here is I need to go to mode and make sure I have my stat diagnostics turned on. Now, this is going to be a negative model, and the reason is because the enrollment appears to keep going downward. So if I go to stat and do a linreg, L1 and L2, and I can actually store my regression equation if I go to vars and choose y vars y1, and then calculate it. Here's the data for this. Now, what I'm going to do here is, copy this picture over to my notes real quick. Okay, number one on the final. I'll tell you what. Let me pause this real quick, and I'll get to talking about the final here. So for the line of best fit, it's always y hat because that's a prediction model, and this is negative 34.87x plus 28.62. And the correlation coefficient R to four places is negative 0.9878. So that's going to be our correlation coefficient R. Now, the practical meaning of the slope, that's actually very easy to do here. Basically, the slope is negative 34.87. This means that each year we expect the student population of Ambridge High School, that's actually Pittsburgh, to decrease by 34.87 students each year. Now, it's decreasing because the slope was negative. If it were increasing, then the slope would be positive. Consequently, it's a negative slope. Now, for the linear correlation test, all you have to do here, for the null, that would be rho equal to 0, and these are always going to be one-sided. And for the alternative, it would be less than 0. Now, the reason it's less than is because we think that this is negative. So basically, the slope being 0 means no linear relationship. And for the slope to be negative, there is a negative linear relationship. Now, what we can do here is we can actually use the t calculation here. So the formula for t, it's actually really easy to do. It is r over 1 minus r squared, square root of 1 minus r squared over n minus 2. and it'll have a distribution with n minus 2 degrees of freedom. Well, since there are 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces of data, the degrees of freedom is going to be 7. I always like to do the t calculation, and t is going to be negative here. Over n minus 2. So we'll do the r calculation. Now keep in mind, r is negative 0.9878. Yes, that is right. So yeah, we set up a fraction right in here. Yep. 1 minus negative 0.9878 quantity squared over n minus 2, which is just going to be 7. And this is going to be negative 16.78. So the p-value, it's going to be 0. We do TCDF from negative 100 to negative 16.78 with 7 degrees of freedom, and that is going to be 0. So basically, since we rejected the null, we have evidence there is a negative linear relationship between the year and student enrollment. Now, based on the model, we're going to predict the population in the year 2025. So keep in mind, that's where t is going to be 25, and in this one, t would be 50. So y hat would be negative 34.87 times 25 plus 2428.62. And of course, we'll round to the nearest student. And that's going to be 1,557 students is what we're predicting. We would be projecting that Ambridge High School will be down to 1,557. And if we do the same thing here for 2050, let's see how many students that's going to give us a prediction of. Yeah, we're down to 685 students at that point. Now, when you can, so you can, based on this model, what you can do now is you can actually predict when the population would fall to 1,500 students. It's going to be after 2025. So you would have to solve the equation 1,500 equal to negative 34.87x. Why is this not working? Negative 34.87x plus 2428.62. So we got to get this solved for x. So we've got to take away 2428.62 from 1500. And we get negative 928.62 equal to negative 34.87x. Why is this not letting me draw my 7? Then we divide both sides by negative 34.87. And we get 26.63. We'll do the nearest one. Come on. Or 27. Now, this would be the year 2027 when this is supposed to happen. Okay. So yeah, 2027 for that one. And basically 500 students, you now have 500 equal to negative 34.87x plus 2428.62. So we'd have to do 500 minus 2428.62, and then we divide by negative 34.87, and we get 55.3. Or 2055. So now we'll give the scatter plot with the line of best fit. So to do that, we can use the graphing calculator. Now, if we go to second and stat plot, we'll go to plot 1. Now, we'll turn it on. Now, if you hit graph, nothing's going to happen. But if you go to hit zoom and 9 for zoom stat, like you've done with box and whisker plots, this is what I'm looking for. So basically, all I'm looking for is a copy of this from your calculator. And with a scatter plot and line of best fit, some of these points are going to be above it, and some of them are going to be below it. So that's all I'm looking for that one. Now, for 2007, we're going to determine the residual for that. Now, the thing we've got to do, yeah, just hand draw it. Basically, copy it from your calculator. Oh, that's shut up. All right, so we need to find the 2007 predicted model. So would be negative 34.87 times 7 plus 2428.62. And we'll round that to the nearest number, 2185. So that's the predicted model of, that's the predicted number of students, 2185. Now, what happens here is to determine the residual is way back. Basically, the residual is the observed minus the predicted. So we have to take the observed value, which is 2155. Observed minus predicted or expected. So 2155 minus 2185. So the residual is negative 30. And that's the answer I would be looking for. All right, so that's how we would do this problem here. So I'm going to record this now. So let's say you start a new company called Conglommo. The years and the yearly profits in millions of dollars. Now, when you have 1,000 million, that is 1 billion, FYI. So, and let X be the number of years since 2000. So we would have like 3, 8, 9, 12, 15, 16, 18, and 19. So what I'm going to do there is I'm going to put this data into the calculator. All right. I'm going to find a good way to do this. Hang on. All right. There we go. That'll do enough for me. No, that won't. There. All right, so what I'm going to do here is, first off, go to Stat and Edit. I'm going to remove, I'm going to clear these lists. Again, do not delete them. So L1, in L1 will go the years since 2000. So, 3, 8, 9, 12, 15, 16, 18, and 19. All right, so the first thing we're going to do is we're going to determine the equation of the line of best fit. So for that, we go to Linreg, and we got Hannah joining the house here. All right, Hannah's in the house. So we calculate that, and there we have it. So what I'm going to do here is I am actually going to just, copy this over. And so to determine the model for the line of best fit, all we have to do there is we have to, it's going to be y hat. If you don't put the hat, that's okay. AX plus B, so it would be 180. Come on, why is this? Don't do this to me today. 180.5x minus 598.1. And the correlation coefficient is R equal to 0.9940. So, in other words, that is a pretty strong linear regression. Now, the practical meaning of the slope. First off, we have to identify the slope. The slope is 180.5. This means practically as each year increases, we would expect our yearly profit, is it profit or revenue? Profits. Profits are good. By $180.5 million. So obviously this is going to be a linear correlation test for positive linear correlation. So the null would be that rho equals 0, and that's indicating no linear relationship. And alternatively, rho is greater than 0, which is a positive linear relationship. Now, so there were 1, 2, 3, 4, 5, 6, 7, 8 pieces of data. So one thing I can do here, since there were n equal to 8, that means our degrees of freedom is going to be 6. Now, I'm going to show you this both ways. So the alpha is 0.05. So let's look here at this table that you should have with 6 degrees of freedom, one tail. Our critical value is 0.62149. So basically, since our R is greater, we reject the null. And henceforth, we do have evidence of, hang on one second here. There we go. We do have an evidence of a linear relationship. Now, that's one way to do it. I would accept that. Now, the other way, if we actually calculate t, which is r over square root of 1 minus r squared over n minus 2, well, that r value is 0.994. We still have 6 degrees of freedom, 1 minus 0.994 squared over 6. So if we do that in our graphing calculator, we get 22.25. Basically, the p-value would just be 0. So it's just more evident that we would reject the null, and we have evidence of a linear relationship. All there is to it. So we're going to predict the profits in the year 2020. Now for 2020, that means t is going to be 20. So the profits for that year, 180.5 times 20 minus 598.1. So you punch that up in the graphing calculator, and we get 3,011.9 million. Now, I would have gladly accepted that, but if you divide that by 1,000, that gives us that in billions of dollars. Wow, we're making some real money. What would you do with that money? Give it to me. I'm just kidding. I don't need that. Oh, yeah. Let's just spread it around. All right, so 2050. Ooh, we're going to have some good money here. Buy more inflatables. Well, what I would probably have to do there is I would probably have to buy my neighbor's yard. And so basically we get 8,426.9 million, or $8.4269 billion. My neighbor actually is talking about like selling his house, and he wants my wife to buy it I mean, it's a nice house, don't get me wrong, but I don't want one with a second floor. I prefer a ranch house like mine. All right, so based on the model, when will the profits hit $10 billion? Well, keep in mind, 10 billion, that's 10,000 million. Dang. So yeah, and the reason we have that as 10,000 million is simply because, remember, 1 billion is 1,000 million. So we set the equation 10,000 equal to 180.5x minus 598.1. So we add 598.1 . So 10,598.1 equals 180.5x. All right, and it's not letting me draw this dang arrow. Okay, here we go. Divided by 180.5. That would be the year 58, or basically rounding it to the nearest one, 59, or 2059. So in the year 2050, we had over $8 billion. So that's what we get there. Now, based on the model, when will the profits hit 1 trillion? Well, 1 trillion is 1,000 billion, which is 1,000 times 1,000 million, or 1,000 times 1,000 is a million. So a million equals 180.5x minus 598.1. We're going to get, this is going to be a rather long time for this, I think. And it will be, x will be 5,543, or it's 2,000 years since then, or the year 7543. So I don't think that's going to happen. In that case, an exponential model would probably be more appropriate if you wanted it to get closer to $1 trillion, but that's how that works. All right, so based on, so the scatter plot below, so one thing I'm going to do here is, I believe the final exam didn't actually ask for it, but I'm actually going to go back to LinReg, store the regression equation to y1, and then recalculate. Now I'm going to go to stat plot, turn that sucker on. Come on, there. And then I'm going to, leave it like that. Now, when I go to graph it, nothing happens. Now, I'd have to hit zoom 9. There it is. So, needless to say, this is a pretty good fit for this. All right. So, last one here, for the year 2018, we need to give the residual. So, for the predicted model, y would be 180.5 times 18 minus 598.1. and we get 20, let's just round this to the nearest whole number, 2651. Now, the actual amount in 2018 was 2732. And for a residual, it is the observed minus the predicted. Observed or actual, so 2732 minus 2651. And the residual is $81 million. So, now another thing before I stop recording here, if you go to Stat and Edit, one of the cool things that this calculator actually does is it stores the residuals. So if you highlight L3 and hit second stat for list, you can choose LResid. Now, if you look here, for the year 2018, there's your residual. So I'm going to stop the record now because that's it. Now I'm going to actually update that video that's on YouTube and include these two examples. I'm going to post that today.